Okay, we're still waiting for a few more people. Hopefully all of you have seen the homework that is out. Have you? I couldn't hear it if you were talking to me. Yes,
Yeah.
okay. Thanks. Okay, so let's start. Good morning, everyone. Hopefully you can all see the first slide, the administration slide. So just want to remind you all, one is, remember that all the lectures are available on the website before the class. Sometimes it's not exactly the final version, but it's close to it. Please go over it, be prepared, be ready with questions, so you'll have less surprises and lectures will be easier to digest. 2, homework 1 was released. Hopefully you've all looked at it. I'm going to spend a little bit of time talking about some of the key issues a little bit later today. It covers a lot of stuff: stochastic gradient descent, decision trees, feature extraction. We are introducing one form of ensemble models that we haven't talked about in class, but you'll learn from it, learn about it in the homework. And we are introducing some methods in experimental machine learning. We're going to talk about it toward the end today and next time, but really, I think that the homework is self-contained and everything that you need to know is there. I do want to urge you to start working on it now. Don't wait until the last day or the last 2 days. You will have questions. It will take time depending on how experienced you are with these kind of things. Start early. Also go to recitations, go to the office hours. That's why we are doing it. Please come ask questions. I want to also remind you that we don't have class on Monday, next Monday, observing Yom Kippur, and those of you that don't, it will give you more time to work on the homework and come with questions. Okay, so as I said, I'm going to attend to the problem set a little bit later today. I first want to try to move on if Zoom allows me. What's happening here? Okay, let's try again. Okay, so hopefully we are back. What have we done? So just to summarize what we've seen last time, we talked about decision trees. Specifically, we talked about expressivity of decision trees, and hopefully we all agree that it's a very, very expressive class of functions. Any function that you want to represent, you can represent with decision trees. This has advantages, but also some disadvantages. We're going to see it today. We're going to see it. You're going to see it in the homework. We gave an algorithm. So we gave a skeleton algorithm that was a recursive decision tree algorithm. You choose a root node, you split based on the values this root node, this root variable takes, and then you keep on down recursively. And then we instantiated this general recursive decision tree algorithm with a very specific method of how to choose the root node. And in order to do this, we introduced the notion of entropy, and we used it to introduce the notion of information gain. And that's going to guide the algorithm. So let's move on to an example. We started with it last time. We're going to do it in more details today. So this is the data set we have. We have 14 examples. For those who don't remember, we have 4 features or 4 attributes: outlook, temperature, humidity, and wind. And these are the examples, and these are the labels. So you can see that we have 5 negative examples and 9 positive examples. With this data, we want to go ahead and try to learn a decision tree. And as we said, the first thing we're going to do is we want to figure out what is the entropy of the data. So we're looking at this column play, the labels, and we're going to calculate the entropy. 9 out of 14 are positive examples, 5 out of 14 are negative examples, and therefore the entropy is the negative of p plus log p plus minus p minus log p minus. That's what we get. Now that we have this, we can try to search for the root tree, for the root node. And essentially, we're trying to do 4 times the computation of the information gain, 1 for each of these, until we get to find which one gives us the highest information gain. And as someone commented, I mean, really, I don't need to know this entropy. I can just compute this and find the smallest value, which is of course true. It's just that it's nice to see the semantics, to understand the semantics of the gain, which split improves the most. And therefore, we just keep this as a reminder of that. So we're going to look at Outlook. Outlook can take multiple values. If it's sunny, then we have 5 examples. Example 1, example 2, 8, 9, and 11. 2 of them are positive, 3 are negative, and that's what the negative, you can see that it splits almost evenly, so the entropy is going to be high. Then we're going to do the same thing for overcast. In overcast, it's very easy because all the examples are positive. You don't need to compute anything. You know that the entropy is 0. Rainy, same split as before, 3, 2. So we know that it's the same entropy. And therefore, we know that the expected entropy, that is the weighted average that I show here on the top right, is going to be this weighted average and this number. And this gives us overall this information gain. So it's a very straightforward computation, but we have to repeat it also for the other attributes. So I'm showing here again the case of humidity. Humidity can take the value high or normal. And hopefully the intuition that you have is this is almost in the middle, 3/7 and 4/7, so it's going to be very high, even higher than what we saw before with the 2/3 split, because this is closer to a half. And this is, on the other hand, very extreme, 1/7, 6/7, it's going to be low. The expected entropy is this, and the information gain is this one. Okay, so I'm not going to compute it for all of them, but you see the idea. We considered 4 attribute: outlook, humidity, wind, and temperature. We computed the information gain, and we chose to split on outlook. Okay, so that was last time, and that's where we are now. So we split on outlook, and we finished the first step, and now we need to go on with the recursive step. So now I have 3 new data sets. So one data set is the outlook equals sunny. This data set consists of example 1, 2, 8, 9, 11, for which it's sunny, 8, 9, and 11. And then I have the overcast data set, another 4 examples, and I have another data set of outlook equal rain, 5 examples. And I'm just going to continue the process that I showed before, this time on each of these data sets. This one is a very easy data set because you can check that when it's overcast, it's only positive examples. So we like to play tennis when it's overcast. So I can immediately say yes. I don't need to compute anything. For the others, I do need to compute, and let's just take the case of sunny here, right? So we have these 5 examples, and I need to consider the other 3 attributes: humidity, temperature, and wind. I'm giving you here the computation. You can see that it's actually a very, very easy computation. I'm starting with this 0.97 that I had before. In the case of humidity, you can see that 3 of the examples that, there are 3 out of 5 are positive examples, 2 out of 5 are negative examples, but they are single labeled. So the entropy is going to be 0. The average, which is 3/5 over times the entropy, which is 0, minus 2/5 times the entropy, which is 0. Basically, that's what we are doing. So now we are choosing among humidity, temperature, and wind. And you can see that this is where the gain is the highest. So I'm going to go down with humidity. And that's basically it, right? So I have to do the same thing for rain, which I'll show the complete tree in a second, but I just want to remind ourselves what we've done. So this is kind of the summary of the algorithm. We asked the standard question, the initial condition: does the data set uniquely define the class? If yes, return this label. Otherwise, find feature with the most information gain. And this is the key operator here, the argmax over all features of the information gain. Add the children to S according to the values of this chosen attribute. Consider the subsets, right? So SK is going to be here, the subset of the original data set with the specific value. So outlook equals sunny, for example, and I'm going to come back and run the same algorithm again. And what we get is this decision tree at the end. Any questions?
Hey, Professor, I have a question.
Yeah.
So entropy is 0 on the sunny humidity because they're all positive. Is that why?
Yes.
Got it.
Right. So again, entropy measures the level of uncertainty. If everything is positive, there's no uncertainty. We just know that all the examples are going to be like this. And the examples that we gave last time, definitely go back to them and convince yourself that that's what you get, and develop this intuition. Any other question? Okay, so just to summarize it at a slightly higher level, what have we done here, right? So it's really a search algorithm, but it's a greedy search. We don't go back. And it's a search in a huge space that really represents all possible discrete functions. This has some advantages, right? Because any data set that you have, we can fit it. We can learn to represent it using a decision tree. It also has disadvantages because every data set that you'll have, we can fit it. We can represent it with a decision tree. And from a learning perspective, this could be a disadvantage because you can basically learn irregularities in the data that have nothing to do with the function that you care about. You can be biased. You basically overfit. And we're going to use this term a little bit later today and explain it in more details. That's one thing. Now, what is our goal here? Our goal is to find the best decision tree. And when we discuss best, you all kind of agree that best means small. Because small is going to guarantee, intuitively at least, better generalization. Now, best can be defined multiple ways. It can be smallest depth. It could be minimizing the expected number of queries, of tests that you have to do on a given example. But either way, this is a hard computational problem. And so it's NP hard. We're not going to do that. Instead, we're doing a greedy heuristic search. Essentially, you can think about it for people that are familiar with search as a hill climbing without backtracking. We just go down or up. We never go back. But we make all the time statistically based decision using the data we have. I'm writing here all data, mostly to trigger your thoughts about it. Is it really all data? Well, it's all data at the beginning, right? So for the first route, I'm using all the data. But once we go down the tree, we don't use all the data anymore, right? We split it and we look at subsets of the data. So as we go down the tree, our decisions are, or our estimates are less robust. And this is, again, something that we want to keep in mind when we think about how we want to improve it. I want to say something about the history of decision trees. It's been around for many, many years, 60 years or so. Like all good things, it wasn't invented in computer science. It was actually invented by psychologists, where they try to basically represent data, experimental data, in a more compact way, but then developed or sophisticated or more sophisticated learning algorithm were developed in the 70s and 80s. ID3 is the algorithm that we are making use of, developed by Quinlan. A lot of systems were developed on top of it, but basically with the same idea. A group of very famous statisticians worked a lot on decision trees, both classification versions that we are talking about and regression versions, which are very similar, only that in the nodes we are allowing real valued numbers. There is a famous book that is called CART for classification and regression trees that is still valid. A lot of work in the machine learning communities in 80s, 90s, and a lot of extensions, how to deal with noise, how to deal with continuous attributes. And we're going to talk a little bit about this and some improved algorithms. So when you're using the Python packages that you will be using for the homework, you will be using a somewhat different versions than exactly the ID3, even though the information gain function is still the same. Now, today in machine learning, most people, where they really care about performance, will not use decision tree as is, but rather they will use collection of decision trees, ensembles of decision trees, and they will ensemble it via various algorithms. One instance of it, a very simple instance, is something that you're going to see in your problem set. I'm going to discuss this in a minute. And later in the semester, we're going to talk about some more sophisticated methods to do this, something that is called boosting, that is theoretically driven and very nicely justified method for combining classifiers in general, but decision trees in particular, or bagging methods. And these together give a very, very good general purpose algorithm. Okay. Questions? Just respond if you have questions. You don't have to respond if you don't have questions. Okay, as I said, you don't really need to say no. I'll take the no as default. Okay, so I guess slow stream, which means we are okay. Okay, so that's a good time. Okay, so could you review how we decide for the second level of decision trees? Okay, I guess that's the same. That's the same question. So let me go back to this step here. Okay, so we decided that Outlook is the chosen one. And we know that Outlook takes 3 values, right? This is what the data tells us. The Outlook, you look at this column, takes the value sunny, overcast, and rain. What I'm doing now is I'm taking this set of 14 examples and I'm splitting them to 3 disjoint sets. One where Outlook is sunny, one where Outlook is overcast, one where Outlook is rain. What I'm giving you here are the indices of the examples in each one of these subsets. So where Outlook is sunny, the example that belong to the subset are example 1, 2, 8, 9, 11. When Outlook is rain, the example that belong to the subset is 4, 5, 6, 10, 14. This data set consists of 5 examples that are split 3 positive, 2 negative. And now in this data set, I'm just repeating exactly the same algorithm as before. And the example that I showed here was, as I said, continue until every attribute is included in the path, or all examples have the same label. And what I do here is I show this example for the case of sunny. These 5 examples, which are highlighted here in blue, are the new data set. The new data set that in the algorithm we denoted as S subscript sunny, or subscript Outlook equals sunny. And again, I'm doing the same thing. I'm computing the information again for which one of the attributes, humidity, temperature, remaining attributes, humidity, temperature, wind. And I'm doing the argmax, which in this case gives me humidity. So I'm adding humidity. Okay, so hopefully that's clear. You should go back to it and convince yourself. And I want to talk a little bit about homework 1. Homework 1 has 2 questions. One of them is a short question that basically tries to get you to go over the details of the algorithm manually, do some computation, no coding, just to make sure that we understand the concepts. I'm not going to talk about it. The second question is the bulk of the homework, 80% of the homework, and it has two parts. The main part is developing some algorithms. And there are 4 algorithms that you're going to play with there. The first one is SGD, stochastic gradient descent. What I'm showing here on the right is a depiction of how you can think about stochastic gradient descent, at least architecture-wise. So we're going to have features. We have 2 data sets that you're playing with, one in 2A and a second one in 2B. In 2A, I believe that the data set has 600 features. So you can think about this simple network, simple neural network if you want, where you have these 600 features here, then you have 600 wires that link it to the root node, the decision nodes. Each one of the wires is going to have a weight, W1 up to W600. These are the weights that your algorithm is going to learn. You're going to initialize it and then use the SGD algorithm to learn it. And at the end, your decision is going to be this dot product here at the root, dot product between the W vector and the feature vector. That's rather simple. We're not asking you to code it. You're basically going to use an existing library, even though in the recitations, you have seen code for it. Go back to the recitation. It's online if you want to just make sure that you understand it. So that's one. That's easy. The next one is decision trees and decision tree stumps. So basically, you are going to use here 2 algorithms. One is just the decision tree algorithm. And as we said, a very expressive algorithm, you will be able to feed the data. And the second one is decision tree stumps, where we limit the size of the decision trees. And I think we ask you to limit it at depth of 4. Here is potentially an example of this decision tree, a small decision tree. So the root node is X7. If it's white, you go here. If it's red, you go here. If it's blue, you go here. And then on the right side, you consult feature X101. If it's small, you say no. If it's large, you say yes. Small decision tree. And you'll experiment with both of them, and you'll see what decision trees give you on the training data and the test data, and what small decision tree, which we call decision tree stumps, give you for on the training data and on the test data. Again, this is the next step is the most interesting step, and the one that will require some conceptual understanding, and I'm going to try to spend a few minutes explaining it. So this is the SGD plus stumps. The idea here is that we are going to use this architecture here that I show on the right, but instead of the original features that we gave you, you're going to use decision trees as features. So instead of this X1 here, we're going to place a 3. Instead of X17 here, we're going to place a 3. Instead of X, whatever number it is, we're going to place another 3. Instead of 600, we're going to ask you just to do 100 trees. So it's going to go until 100, and the number of weights that you have here is only going to go up to W100. Now, so that's what you're going to do here. But you have to ask yourself a question here. Decision tree is a deterministic algorithm. I gave you data, these 1,000 training examples, and I ask you in the second bullet here to learn a decision tree and then learn a decision stump. It's deterministic. You learned one decision tree. How come I'm asking you to get 100 here? Now, if all of them were the same, it would be boring, right? I don't need to write all of them. So what's going on here? how do we get 100 different features? All of them are decision trees. So the key issue is that in order to get this diversity, we're going to run it on different data. Specifically, what we ask you to do is to choose just half of the features randomly. So out of the 600 features in this case, or in 2B, it's going to be 260 features. You're going to choose randomly 50% of them, learn a decision tree, a decision stamp. Do it again, choose 50% of the features, learn a decision stamp, do this 100 times. This will give you 100 features, 100 stamps. Once you have these 100 stamps, what is going to be the process? By the way, it's not the only way to do it, right? So you definitely need to run on different data, but accomplishing this can be done multiple ways. You can do it by choosing half of the features, as we suggest here. You can just choose half the data, keep the same number of features. In this case, we suggest that you do this. But still the question is, okay, so you've learned 100 decision trees and the decision trans. What are you doing now? So here's the process. Once you have this, the process is that of transforming the feature space. And this is what you're going to do. For each example, I'm writing it here as X from 1 to 600 because this X has 600 dimensions. You're going to convert it to the following 100-dimensional examples. You take this X, evaluate decision tree 1 on it. You take the same X, evaluate decision tree 2 on it. The same X, evaluate decision tree 100 on it. Now you have a vector, which is the prediction of each one of the 100 decision trees on example number 1. And you do the same thing for example number 2 and so on. For your 1,000 examples, you're going to do that. So now you have a matrix, if you want, of 1,000 by 100, where each row represents the new features, which are the predictions of your decision trees, small decision trees on this example. Once you have this new data set, you can run SGD on these 100-dimensional examples. So that's what we're doing here. Questions? I see one question on the chat here. Does SGD plus TAMS mean AdaBoost decision trees? No. AdaBoost is a more sophisticated algorithm. We're going to get to it in a few weeks. This is a simpler way of using decision trees as features. Something that you can do already in your second week into a machine learning class. And yes, we are using, in this case, 50%, that is 300 of the 600 original features for the first data set. Any other questions on this? Okay, excellent. So, so let's move on. The next thing I want to talk about is introduce the notion of overfitting, which is really important in decision trees in general, in decision trees and in general in machine learning. So here's the decision tree that we learned. Okay, I see a question. I want to go back to it. Can you explain the final step? So let's see. So hopefully it's clear how to learn 100 decision trees. Now, but the key step is really what's here in this yellow rectangle. So I need to convert the data. I start with 1,000 examples, say. Each one of them is 600 dimension. If you want, you can think about it as a matrix of 1,000 by 600. By the way, you're going to do this for the training, but you're also going to do it later for the test set, but it's going to be exactly the same process. You want to convert this to new examples. So for each example, each row in your matrix, which looks like this, it's X with 600 dimensions. You're going to convert it to the following 100-dimensional example. And the way you're going to do it is you're going to run the decision tree, the first decision tree on X. And then you're going to run the second decision tree on X. Finally, you're going to run the 100th decision tree on X. That's for the first example, X. And this gives you a new example that corresponds to X, but it's only a 100-dimensional feature, 100-dimensional example, whose feature values are the output of the decision tree, the 100 decision trees that you have on X. And then you do the same thing for each one of the X's, and you get 1,000 examples. Each one of them is 100-dimensional. And in the first coordinate of all these examples is the evaluation of the decision tree number 1 on each one of the examples. Okay? It's non-trivial. You have to think a little bit about it, what it means, how to do it, and of course, how to implement it. So this is the part that you will implement. Hopefully, this will make sense and will make even more sense when you see the results. Okay. That's the tree that we learn, whether to play tennis or not. And here is a new example that came in. The example says outlook is sunny, temperature is hot, humidity is normal, wind is strong, and the label is no. Now, if you look at the decision tree that I put here on the right, it doesn't fit, right? It, in fact, is inconsistent with the decision tree. But that's no problem for decision trees. I'm going to augment the decision tree. Now I represent this example too, right? So I had to condition, I had to add a condition here because I went down with outlook equals sunny. And then when I asked on humidity, normal, before it says yes, but this example says no. So I have to add another condition. I'm conditioning on wind. If it's strong, it's no. So this path is the new example. Now, the issue is that I can always do this. Decision trees are very expressive. So as long as the data set isn't inconsistent in the sense that this exact same examples have 2 different labels, I can always do this. But this may not be good because I can fit noise, I can fit other coincidental regularities and biases in the data. Maybe we don't want to do it. In this case, we can say that we overfit. So let's just take a slightly higher perspective on this. So this is the space of all data we have. But what we observe in our training data is just these red and green points, the labeled points that we were given. Green and red labels. In fact, there's a lot more data out there. These white examples are examples I haven't seen. I don't know what their labels are, but it's out there. And what we've seen is just a small sample of this. If we take these labeled examples way too seriously, maybe we'll not generalize and will not predict correctly on future data. Quantitatively, we can think about it this way, right? So if we plot the accuracy of our model, our learned decision tree, as a function of the complexity of the tree, say the size of the tree, then On training data, this red curve here, we're going to improve all the time until we finish touching all the data. But on our test data, say we set aside some data, sometimes we're going to do it with a validation set. Sometimes it's just going to be the test data. We are going to improve as we grow the tree until certain point. At some point, we're not going to improve anymore. In fact, we're going to degrade on test data as we improve on the training data. This is the point where we actually want to stop training because we overfit. And you'll see this very, very clearly when you play with your data in the homework. So basically, there's too much variance in the data. The training data is not necessarily a perfect representative of the whole instance space, right? Someone gave us a sample, not necessarily a perfect representative. And because of that, we split on features that are actually irrelevant. There could also be noise in the training data. When we say noise here, we can mean one of two things. Either the feature value is wrong, we measured the temperature, someone called it hot, actually it was cold, there was a mistake in the feature value, or when someone assigned the label to the data, to the example, they assigned it a plus, it should have been a minus. And because we believe this data set, we will predict on noise. We will fit the noise. In both cases, because we are driven by trying to minimize the empirical error, right? We care only about how we behave on the training data. We learn too much. And decision trees are expressive enough to allow us to do this. So we have to do something in order to counteract this. And in the case of decision trees, what we do is we do pruning. We basically say, you know what? Even though you can feed the data, if you grow the tree large, I'm not going to grow the tree that large. I'm going to remove leaves and sometimes just assign a majority label instead of completely splitting it. And you can do it in multiple ways. One procedure that makes sense here is prune the children of a node S if all the children are leaves. I'm going to prune leaves. And the accuracy on the validation set, so a set aside data set, doesn't decrease if we prune it and just assign the most frequent class label to all the items in this node. So this is not the only way to do it, but this is one way to do it. So, and really there are two basic approaches for pruning. One of them is pre-pruning. From the beginning, I decide that I'm not going to grow the tree too deep. I'm going to stop growing the tree at some point based on some stopping criteria. It could be just the size. Like in the homework, you're not going to grow it more than depth 4, or based on some performance on some set-aside data set. Or I can do post-pruning. So I'm going to learn the whole tree and then go to revisit the tree, go from the leaves and start removing leaves and nodes that I believe do not have enough evidence to support them. Because as we said, while in decision trees, when we choose the root node, we use all the data. As you go down the tree, you use smaller and smaller data sets. So your statistical confidence in the decisions goes down. And you can do this in using various tests. You can use cross-validation. This is something that we're going to mention maybe later today, definitely next time, and you will see it explained in your problem set. So this is one of these things that you will actually learn from the homework. Hopefully you learn many other things from the homework. And you can do some statistical testing. And I'm not going to go to the details here, but you can imagine that I can test whether the observed regularity that I'm fitting now is likely to occur by chance or others. And there are several other methods for doing it. that you can find in the libraries. We don't need to attend to this. But really the goal is clear. The goal is to guarantee or improve generalization. And it's really related or an instance of a general notion that we're going to mention several times in the class, the notion of regularizations. Basically, keep the hypothesis simple, because simple will give better generalization. Okay, before we get to this detour, I want to think about another classifier. We talked about linear classifiers already. We're going to talk more about it starting 2 weeks from now. But SGD and GD are linear classifiers. So are we doing pruning or are we doing regularizations also in the case of linear classifier? And what does that mean? So here is a data set. I'm showing it twice. You're not seeing double. So we have red examples and blue examples, and I can separate it. Here is one hypothesis that separates them. Here is another hypothesis that separates them. Look carefully at this. And think about which one is better, and also why. So this is the question that I'm asking. Which hypothesis is expected to be better, H1 or H2, and why? So as you respond to this, I'm showing you again the hypothesis. Maybe subtle, but we should be able to provide an intuition for why this is the case. Okay, so let's see what you guys think now. Okay, about half of you have already responded. Let me wait a little bit more. Okay, so what do we think? We think H2, but I wonder why. H2 appears more aligned with the data, so I'm not sure exactly what aligned is. Both of them separate the data perfectly, right? So I should have taken a different format and count your votes. I see that H1 is definitely in the minority here, but I want to see more Ys. Lower mean squared error. That's probably true, although it's hard to tell from the picture. At least I don't know how to compute mean square error so quickly. Okay, the margin is larger. That's a good answer, and we'll see in a second why. There's more space on either side of the line. Okay, I like this answer because it gives us exact details using terminology that we all understand. There's more space on either side of the line. So let's move on and see that. So as we said, both H2 and H1 separate the data. So the empirical error is 0 in both cases. And I could also move, one example from one side to another. The idea here, by choosing H1 and H2, I chose them so that on the training data, they behave exactly the same. However, what is the difference here? The difference here is that H2 can be viewed as a thicker separator. So I can give some thickness to each separator. Just like this, they have thickness 0. But I can imagine that a linear separator comes with some thickness. And in the case of H2, I can fit a thicker separator. We can call it a margin. We are going to call it margin later, but basically the idea, there's more space on each side of H2 than there is on each side of H1. And that means that in future data, when we see a future example that we haven't seen so far, the likelihood of a red example crossing this thick separator and moving to the other side, being labeled incorrectly as blue, is smaller in the case of H2 than it is in the case of H1. So this is going to be a better separator. And this is another tool for preventing overfitting that we use in linear classifier. We're trying to learn classifiers with margin, or if you want, thick classifiers, thick linear separators. We're going to talk about this in a very technical way when we get there, but hopefully the intuition is clear. Now, with this at hand, once we understand decision trees, and we already talked a little bit about decision trees and their way of dealing with regularization or with overfitting, I want to extend decision trees a little bit and just attend for a few minutes to a few extensions, because we talked about the basic algorithm, which is for discrete labels and discrete categories. You can do more. So for example, you often want to deal with real valued attributes. Now, one way, the simplest way potentially, is to, in advance, discretize into ranges, right? So I can, if I have size, I can say big, medium, small. Originally, I'm going to transform my data, instead of giving me a real number for size, to give me three values. One is big, one is medium, one is small. That's easy, and then I continue with the algorithm. But sometimes you don't know ahead of time how to discretize the data, because the discretization of the data sometimes has to depend on the labels. Maybe none of the examples are big. So why do I care about this? So a better way would be to develop a splitting node, to split the nodes based on thresholds that depend on the data. So I'm going to use thresholds of the type A less than C that split the data into examples that satisfy A less than C and A greater than C. And I'm going to do it in a way that depends on the data. Once I do this, the same information again is going to hold, right? Because essentially, I can count how many examples satisfy the condition, how many do not, just the same as in the discrete case. So how do I want to find a split with the highest gain? So for each continuous feature A, I'm going to sort the examples according to this value, A, and I'm going to look at the labels. For each ordered pair X label Y with different labels, I'm going to check the midpoint as a possible threshold. For example, I have length here. I have length here as my continuous parameters. So I sorted the examples according to this feature, and I'm looking at the labels. 10 is negative, 15 is positive, 21 is positive, 28 is negative, and so on. Then I'm deciding that a reasonable place to place thresholds to discretize is when I change labels. I'm assuming here, doesn't have to be so, but I'm assuming here that between 15 and 21, everything is positive, so I don't need to do anything. Of course, I could be wrong, but it's more likely that I have to decide between 10 and 15, so I chose 12 and a half, between 28 and 32, and between 40 and 50. So now I have these splits, and I can continue as usual. I have the feature of length less than 12.5. I have the feature of length less than 24.5, and I have a feature of length less than 45. Questions on this? There's one other interesting thing here. You could have also split it to disjoint features, completely disjoint features. Notice that if the number here, 8, if the length is 8, both this feature is going to be active, the length less than 12.5, and the feature length less than 24.5, and the feature length less than 45 are going to be on for the case where the value of L is 8. On the other hand, if the value of 8 is 30, if the value of length is 30, only this guy, less than 45, is going to be on, and these are going to be off. And this actually is an encoding that makes a lot of sense, because the algorithm doesn't know that 12.5 is less than 24, less than 45, less than 100. It doesn't know these numbers. And by encoding it this way, you kind of tell this to the algorithm, because for very low values of L, all these are going to be on, all these features are going to be on. For some values, some of them are going to be on. For some values that are above 45, none of them is going to be on. So in this way, you kind of provide information to this discrete encoding on features about size. Okay, so that's one trick that we've done, dealing with finding splits of continuous attributes. And then as we agree, hopefully the algorithm goes as usual. Let's look at another interesting case where we need to extend the algorithm, and that's the case of missing values. Many times values are not available. Let's take medical diagnosis, where we're using decision trees. Sometimes values are not available because tests were not done. Sometimes they're not available because some tests are expensive and we decide not to do all of them. But in all these cases, what you will get is you will get examples that are missing some values. And the question is, how can we train on this? How can we evaluate the information gain when in some examples, we don't have a value for one of the attributes, A in this case? So let's consider this case where we looked, the case we looked at before. We already learned that Outlook is the root node. And now we're trying to figure out what happens below. We're looking at the subset of Outlook equals Sunny on the left side of the tree here. But one of the examples here is missing a value for humidity. What do? How can we compute the information gain where we are in this situation? Suggestions? Basically, guess is a good option, but we want to guess in a way that makes sense. For example, I could go with the majority here, even though the majority here, there's a tie, so it doesn't matter. I can choose high, I can choose normal. So when I get to humidity, I can just fill in the value, assign the most likely value of the feature to S. In this case, for example, I chose normal, and I computed the entropy based on normal. But there's another way of doing it, which is to use fractional counts. Now, no one said that the entropy has to take integer values into the computation, right? I can compute it as if out of the 5 examples that I have here, 2.5 are high and 2.5 are normal. The computation just continues the same, right? So you can plug in into the entropy formula a fractional number. And this potentially is the best way to deal with this, right? So I'm basically approximating a value for this. Any other suggestion that you can you can make here. I can drop the data, and if I have really a lot of examples and only one of them as a missing value, I can do this. But in general, I don't want to drop data because it does have value. But instead of dropping the data, as someone is suggesting in the chat, I can look more carefully at the data. So look at this data set more carefully and give me another suggestion. If you were to guess, what would you guess here? What's the value of humidity for this example? Why high? I see a lot of suggestions for high. Someone can take, unmute themselves and make a suggestion. Okay, so I'll make the suggestion instead of, okay, someone wants to do it? Well, you can look at the data and you can see, for example, the label is no. The normal examples are all yes. So maybe it should fit with the examples number 1 and 2 rather than with 9 and 11. So essentially, I can learn from the other attributes that I have what is a reasonable value for this, and then fit it in and keep on learning. So essentially, the other pieces of information in the data could provide some perhaps more informed guesses for what this could be. So this is another learning problem inside our learning problem. Learn how to complete this missing value, use the output of this small learning problem to put here a value and keep on learning. And sometimes we can do this. We're going to develop a very general learning algorithm that does that. It's going to be called EM, expectation maximization, where the idea is a principled way to deal with missing values. We have to make some more assumptions in order to completely justify this, but it's a very general procedure to deal with these missing values. In this case, we don't have to do it. We can just say, okay, I'm going to make a guess as informed as I can and move on with it. Okay, so we dealt with the case of missing value in training, but we also have to deal with missing data in testing. So someone gives me an example, I want to classify it, but I don't know the value of attribute A. So here is my tree. I'm getting this example. Sunny, hot, unknown, strong, and I need to guess the label. I need to predict the label. Now I can go down the tree. Outlook is sunny, and then I get to humidity and I don't know what to do because I don't have a value for humidity. So what's the solution here? So really don't know whether humidity is normal or high, and therefore I don't know whether the label is yes or no. Even worse, maybe outlook is unknown. So it's very difficult to start even computing it. So in these cases, you want to be able to marginalize if you want. I'm using a probabilistic term for something that isn't probabilistic over the options that I have. For example, in the case of Outlook, I would say, you know what, I have no idea what this is. I'm going to say, with a probability a third, I'm going to go this way and continue. I'm going to get yes. With a probability of third, I'm going to go this way. I'm also going to get yes. With a probability of third, I'm going to go this way. I'm going to get no. my prediction is yes. And you can generalize this procedure to any step you are at the tree. Basically, split it on the various options that you have. In this case, I split it evenly. Really, I should have split it as 5 out of 14, 4 out of 14, 5 out of 14, rather than exactly a third. But hopefully you see the point. Questions on this? Okay, so there are many other issues that we want to address when we deal with decision trees. And basically what I gave you here is, in these 2 lectures, is kind of the basics. For example, you may want to change the way you compute information gain. Maybe you have attributes that have different costs. Some of them are more important to you. You really want the decision tree to emphasize them more. So you can change the information gain so that you prefer some of the attributes. Maybe some of the attributes have a lot of values and some of the attributes have very few values. In our case, all of them had 2 or 3 values. But when you have this kind of extreme values, extreme numbers of values, some of them are very small, 2, some of them could be 10 or more. When you play with the information gain metric, you will see that it actually prefers those with many values. Because the entropy values, as we've seen in an example last time, are going to be higher, kind of its log of the number of values. And therefore, information gain is going to give more weight to those attributes that take multiple values. Maybe you don't want that. Maybe you want to deal with it a little bit differently and scale down the information gain. So again, algorithms exist. If you play with the existing libraries, you'll see that they have tons of options to deal with these kind of things. One extension that is very interesting is that of oblique decision trees. So the way we think about decision trees is really as axis parallel things, right? So when I talked about continuous variables, I'm just going back here to show this. The conditions that we had are A less than C or A greater equal than C. So essentially you can think about it as axis parallel things. A is greater than something or smaller than something. But you could imagine, and decision trees basically split the space to axis parallel boxes. But you could imagine that you want to split it diagonally, right? To that rather than A is less than C, say you have 2 features, A and B, you want to know that A plus B is less than C. Or maybe A plus 2B is less than C. So it's a splitter that is not parallel to the axis. This is what oblique decision trees are doing. They split the space. I'm going back there. Oblique decision trees are dealing with root or nodes decisions that are not of the form A is less than C, but rather they will put a linear condition there. 2A plus 3B is less than 5, where A and B are your features. So the decisions are not axis parallel. Now, of course, this adds another complication. You have to first decide what combinations should I put in a node. How do I learn how to weigh the features to learn good conditions for the node? So that adds another layer of learning here. We're not going to talk about it, but it's good to know that this exists in case you want to do it. And the final issue I want to present is incremental decision trees. So the way we talked about it is a batch algorithm, right? So I gave you the data set. That's what you're going to do in the homework. We gave you a fixed data set. You learn, and you're done. Now, you could imagine that there is a stream of examples. So you start learning the decision trees, new examples come in, you want to keep learning and potentially update the decision tree. So one of the issues that happen in this case is you want to maintain consistency. You know, perhaps example number 101 that came in has label plus, but if you were looking at the decision tree that you learned so far on the first 100 examples, you would predict negative for this example. So you're not going to be consistent. You want to change something as a function of this new example. And of course, you have two extreme solutions. One example is ditch the tree. Let's just learn again on the 101 examples. Maybe not ideal because you don't want to do it every time. So people have developed incremental algorithm for decision trees where we are going to basically on the fly try to update this decision tree. Okay, just to summarize what we've done so far, we talked about decision trees, a very expressive, flexible class of functions. We have an algorithm where the key step in the algorithm is based on entropy. We talked about overfitting. We're going to keep on talking about overfitting because it's a really important issue, and we're going to look at it in a somewhat less hand-wavy way. We talked a little bit about extensions, and we didn't talk yet about evaluation in machine learning. You're gonna spend some time on it in your homework, and we're going to talk about it in the next lecture, which, as I want to mention, is not going to be next Monday, but rather next Wednesday. The final note I want to make: we are also talking about decision tree as features. You're going to play with it in your homework, we'll understand it. We'll talk a little bit about it later in the semester too. Okay. So that's basically what we've done. Questions before we finish for this week? Oh.
Hi, Professor.
Yes.
I just have a question about, I think it was slide 70, the continuous attributes example.
Uh-huh.
Why wouldn't 30 also be a threshold, as that's the, I guess, the average of the pointwise between 28 and 32?
If 28 and 32 had different labels, then I would put 30 also. It could be that I just missed it. So the procedure that I was proposing was sort the examples, align them with the labels, and whenever you see a change in the label, put a splitting point there. So if 30 was like that and I just missed putting it, then you made the right observation. 30 should have been also a splitting point.
Okay, thank you.
Was that the case?
Yes.
Okay, so just to finish, we wanted to see what you think. Okay, so I see mostly positive things. If you do have either positive feedback or negative feedback, please let us know. Piazza, in the individual emails, any other way, we want to get it. Okay, so we're done with this. Have a good weekend. Please start working on the homework. Don't wait, and ask questions. Thank you very much, and we'll see you next week. Bye.
Thank you.
Thank you.
Thank you.
Thank you.